Another problem that comes under the Stokes problems is harmonic oscillation of infinite plate. So this is one of the examples of exact solutions again. And remember that earlier we had discussed Stokes problem with respect to time, the sudden impulsive motion of a plate, and in this case the motion that is generated is harmonic oscillation of the infinite plate. The problem is defined to be harmonic, and the fluid motion generated by the periodic oscillation of the infinite plate in its own plane, it can be obtained by imposing the following boundary condition on equation 13. So you can remember, you will recall that the harmonic motion in physics, for example, the movement of a wall clock is considered to be harmonic when its pendulum is moving from right to left and left to right. So that is periodically traveling the same distance every now and then, and that period in which it completes one cycle is fixed. So that kind of situation is here, and therefore, and that is normally whenever we are discussing harmonic motion, the solutions will reflect cosine and sine functions. So that is why here the boundary condition chosen, the velocity is taken as u is equal to u infinity, that is u infinity is some constant value, and cosine of omega t, omega is the angular, and at y is equal to 0 and u is equal to 0 when y tends to infinity. And omega here is the circular frequency of oscillation. The solution is found to be, can be written as this. You will remember that this is a standard way of writing harmonic solutions of functions that are reflected in sine and cosines. And we know that cosine of x plus I sine of x can be written as e to the power iota x, where iota is equal to -1. The same kind of procedure is adopted here, and we obtain u to be the real component. And when we take the real component, what will we get? We are going to get like this, the cos of the function that was written. So this is what is cos. Cos is the real component of the imaginary number of the imaginary value, and u in total is reflected by this value. This, by the way, is cos. And the shear wall is given by naturally this value with the same omega is the frequency of oscillation, t is the time, and tau w is the shear at the wall that is given. So the phase lag between the velocity and the shear is this angle pi by 4, and pi by 4 is equal to 45 degrees.